Okay, so hello everyone. I'm going to talk about some work that we have done with Thomas Jensen and Benoit Montaigu on how to do abstract interpretation for programs that manipulate algebraic data types. So our goal is to have an analyzer that is able to look at the code of a function. Don't try to read it for now, I'll come back to it. So to have an analyzer that is able to look at the code of a function that manipulates algebraic types, and that is able to compute from it a summary of the function in a way that is able to over-approximate the input-output behavior of the function. So one way to look at this is that we are trying to guess the specification of the function in a way. Okay, so and so one of the challenges is that we are trying to do this when we have algebraic types. So what is an algebraic type? An algebraic data type is a type that can use sum types and product types, and they can be embedded inside one another. So a sum type is a type that has multiple possible constructors, and each constructor, each value of a sum type uses only one constructor. And a product type, on the other hand, is a type that has multiple fields, and each value of a product type has to define a value for all the fields. And so if we look at an example of an algebraic data type, we can have the process type here, which could be used, for example, in a simplified operating system to model the status of a process. So here, for example, a process can be either asleep, in which case it has some seconds left to sleep, and the number of times that the process has been activated. Or here, the process can also be running, in which case it only has the number of times it has been activated. And in this work, we do not handle recursive data types. We only handle non-recursive data types, like the one that I showed here. And so now, if we look at what kind of functions manipulate those types, we can have, for example, the tick function that is on the slide. So the idea of this function is that we take a process as an input, and we also output a process. And we're going to look at the input process to see whether it is running or asleep. If it is running, we return the same process unchanged. But if it is asleep, we distinguish two different cases. Sorry. Whether it still has some seconds left to sleep, in which case we return a process that is asleep, but that has 1 second less left to sleep. Or if there are no seconds left to sleep anymore, we return a process that is running, but in which the activation count has been incremented. And so for this kind of programs, we want our analyzer to infer the input-output behavior of the program. So here, the properties that we would like our analyzer to infer are basically the same ones that I already said aloud when explaining what the function does. So we want our analyzer to be able to tell us that a running process is not modified, that a sleeping process with some seconds left to sleep remains asleep, but the budget is incremented, and that otherwise the process wakes up and the activation count is incremented. Okay, so for building our analysis, we start by taking an abstract numeric domain, D, that could be, for example, octagons or polyhedra, and we extend it 2 times in order to reach the abstract domain that we want. So numeric abstract domains are well suited to abstract sets of states in which every variable holds a number. So we extend those domains a first time with an extension that we call the structural lifting, so that now we have an abstract domain in which the abstract values concretize to sets of states, but in which the variables now hold values of algebraic types that I call here structured values. Then I extend this domain again with an extension that I call the relational lifting in order to have an abstract domain that abstracts input-output pairs of states in which in each state, each variable holds a structured value. And so this is how I reach an abstract domain capable to talk about input-output behaviors and about algebraic data types. So in the first lifting, we actually proceed in multiple steps. So we start by taking what I call the numeric path relations lifting, which is going to allow us to talk about numeric constraints about the numbers that are contained in the structured values of our program. Then we complete this domain by taking a product with two other domains. A domain to talk about when two structured values are equal between each other. So this domain, we call it sec for structural equalities. And a domain that talks about which constructors have been used for each one of the sum types. So this gives us a product domain that we then reduce, and we take a disjunctive completion over it. So this is how we build our abstract domain. And so in this talk, I'm going to first talk about the main idea behind the numeric path relations lifting. Then I'm going to talk about why we need to take a disjunctive completion. And then I'm going to talk about why we take a product with structural equalities, and how this structural equalities domain helps us keep the disjunction small. Then I'll go back to the NPR lifting to give a little bit more details on how we analyze assignments. And then I'm going to talk about the relational lifting so that I can show you the whole domain, and in particular, show you what results we get on the running example that I presented, what properties we have proven, and what results we get for our implementation. Okay, so the main idea of the numeric path relations lifting is that we use projection paths in order to point to the numbers that are contained inside our structured values. So for example, if we have a value proc here, which contains a process that is asleep, that has 42 seconds left to sleep, and that has been activated 7 times so far, we can, inside this value proc, we can follow the path at sleep.seconds, and we reach the number 42. Or we could follow the path at sleep.count and reach the value 7. And so using these projection paths and using pairs of a projection path and a variable, we're able to express the kind of constraints that we want. So for example, we could express a constraint that proc at sleep.seconds is positive, for example. And so our abstract values really are abstract values from the underlying numeric domain, but in which the variables have been replaced with pairs of a variable and a path. These pairs of a variable and a path, I'm going to call them extended variables during the rest of the talk. And our paths are defined inductively, so it's either the empty path, or an access to a field, followed by the rest of the path, or an access to a constructor, followed by the rest of the path. The access to the fields are written with dots, and the access to constructors are written with an arrow sign. Okay, and so not all projection paths are defined all the time. And so, for example, if we take again the value proc and we try to follow in it the path at running.count, that wouldn't be defined, because value proc was not built using constructor running, it was built using constructor asleep. And so, even more, if there are some paths that are not defined, there are also some extended variables that cannot be defined at the same time. There are some extended variables that are incompatible. So, for example, proc at sleep.count and proc at running.count, there is no value for which these two extended variables make sense at the same time, because a structured value is either built with a constructor asleep or constructor running, but it cannot be built with the two of them. And so, since the extended variables can be incompatible between them, we need to take a disjunctive completion when we want to talk about incompatible extended variables. So, for example, if we come back to our tick function, two of the properties that we wanted to capture over this function is the fact that if the input is running, then it is not modified. But if it is asleep and has no seconds left to sleep, then it is activated again.
Can you say where we got muted? Sorry about that. Maybe just keep going, I guess. Okay, can you say how far back we need to go? Do you know where it started getting muted? You can just keep going.
Okay, yeah. We'll keep going.
How do you make it full screen? How do you make it full screen? How do you make it full screen? You know?
Okay, yes. So as I was saying, some of the properties that we want to capture involve constraints that use incompatible extended variables. So because we want to talk about p1 at running.count, but we also want to talk about p1 at sleep.seconds. And these two extended variables cannot be defined at the same time. And if we had an abstract value that tries to use them both at the same time, then the concretization will be empty, which is not what we want. And so what we do is that we take a disjunctive compression, which means that we, instead of using a single abstract value, we use multiple abstract values, and we give a disjunctive meaning to this set of abstract values. And that way, we can keep the extended variables that are incompatible in different abstract values, and that way we can capture these properties, even though they talk about incompatible cases. Okay, but so now we have a new problem, which is that which is that in theory the disjunction can grow exponentially, and so if the disjunction grows too much, that will be a problem for performance. So we need to keep the disjunction as small as possible, and for that we do multiple things. One of the things that we do is we try to remove contradictions as soon as possible. And well, contradictions can come from multiple sources. They can come from numeric constraints that contradict each other, for example, but they can also come from extended variables that contradict each other in the same case, which would basically be unreachable branches in a pattern match, for example. We also merge two cases if they talk about the same extended variables. And we also use the domain for structural equalities to keep the disjunction small. So I'm going to explain what the domain for structural equalities is and how it helps to keep the disjunction small. So let's come back to the process type that I showed before. For processes that are either asleep or running. If at some point in an analysis we want to say that two processes, P1 and P2, are equal, then if we only use the NPR lifting, we would need to distinguish two different cases, because we would need to distinguish the case in which both processes are running and the case in which both processes are asleep. And in the case where both processes are asleep, we even would need multiple constraints in order to state that the processes are equal. Multiple constraints for the different fields involved. Whereas if we introduce an abstract domain that keeps track of when two extended variables are equal, then a single constraint in this domain, a single structural equality, allows us to have the same information, and hence it avoids having to consider multiple cases. And so it keeps the disjunction small. Okay, so I've talked about the main idea behind the NPR lifting, which is having pairs of a variable and a path. I've talked about why we take a disjunctive completion and how structural equalities helps us keep this disjunction small. Now I'm going to go back to the numeric path relations lifting and see some of the details of what we need in order to analyze an assignment. Okay, so if we have a program that does 2 assignments in a row, for example, so here, for example, if we have a variable proc and that we start by assigning to it a process that is asleep, that has 0 seconds left to sleep, and that has been activated 41 times, and then we assign again to the same variable, but now a process that is running with a count that has been incremented. What are the properties that we get? Well, after the first assignment, we might get 2 properties: the fact that proc@sleep.seconds is equal to 0 and proc@sleep.count is equal to 41. And after the second assignment, we might get the property that proc@running.count is equal to 42. And so if we look at the second assignment, we might notice something interesting, which is that in the program, there is only one variable that is being assigned to, but in the properties, it affects 3 different extended variables, because we have 2 extended variables that disappear and 1 extended variable that appears. So that shows us some of the things that we have to take care of while analyzing assignments with the NPR lifting. And so I'm not going to give you the exact formula for analyzing assignments, but I'm going to give you the main ingredients that are involved. So when analyzing an assignment, we decompose it into smaller assignments for which the right hand must be either a numeric expression or an extended variable. And so that explains in particular why we end up with multiple extended variables. But we also use intermediary variables when analyzing assignments. Here, for example, when we assign to variable proc, we introduce an intermediary variable that might be called, for example, proc prime, which must be fresh to the program. And this allows us to do 2 things. This allows us to keep separate the extended variables before and after the assignment, so that they don't get mixed up. And it also allows us to exploit the information before the assignment, even though it will disappear. And so we do the analysis as though it is variable proc prime that is being assigned to. And then when we have all the information we want, we remove the old variable proc and all the extended variables that come with it. And we rename proc prime and all the extended variables that go with it into proc. Okay, so I've talked about the NPR lifting, structural equalities, and disjonctive completion. Now I'm going to talk quickly about the relational lifting, so that I can then go to talk about the analysis and the result we get from it. Okay, so the main idea of the relational lifting is, well, it's actually folklore, is the idea that if you have an analysis that computes properties for one single program point at a time, and you want to turn that into an analysis that computes properties between 2 programs points, an input point and an output point, a way to do it is to duplicate the number of variables that you have. So, for example, if you have 2 variables x and y in your program, then you might use variables x and y to talk about the variables at the input program point, and use copies of those variables, x prime and y prime, to talk about the variables at the output point. And then you would be able to use that to express properties between the input and the output. So yeah, so in the community, this is considered a folklore result. But when we looked whether it had been formalized, we didn't find actually a formalization of it. And in particular, we didn't find the formalization of it for abstract interpretation. So we did it. We formalized this folklore idea in the particular case of abstract interpretation, which means that we had to well, yeah, we had to prove that it actually works, and we have to write the formulas that go with it. And what we learned from it is that, well, the folklore works, and the reason why it works is because when you write the collecting semantics well, the collecting semantics with and without the duplication of variables, you get the same inductive decomposition. So the semantics are not the same, but when you decompose them inductively on the different instructions of the program, they verify the same inductive properties, except for assignments and conditionals. But for assignments and conditionals, there is a generic way of writing those for the case where you duplicated the variables, and generic in the sense that they do not depend on the abstract domain that is being assigned. And so that is why the folklore works. And so using this, we turned our abstract domain into an input-output abstract domain, and so we were able to do an analysis that does what we want, that is able to compute summaries for functions. And this also helps us keep our analysis modular, because we can analyze each function only once, and then each time the function is called, we instantiate the function summary that we get, so that we do not analyze the function again. And so, for example, for the tick function that I presented earlier, our analyzer gives us back a summary of the function that relates any input p with the corresponding output p prime, and that distinguishes 3 different cases in the disjunctive completion. And so these 3 cases correspond to the 3 properties that we wanted to prove. And in some cases, it is the structural equalities domain that captures the information that we wanted. So for example, p at running equals p prime at running. And for the other cases, it is the NPR lifting that allows to capture the information that we wanted. Okay. So yeah, so I've talked about the fact that we developed an analysis from our abstract domain. So, well, since we talk about analysis, that means that we chose a language to analyze. So for now, we took a while language that we enriched with algebraic data types. And so even though we took a syntax that is close to the while language, our language actually has a lot of functional properties. So we took, for example, immutable data types. We do not have any global states and so on. So even though the syntax is imperative, the characteristics of the language are functional. We gave this function the usual small step semantics. We defined an input-output collecting semantics with it, and we proved that our analyzer, when given a program C to analyze, starting from the identity relation, using our abstract domain, it does yield an over-approximation of the input-output semantics of the program. So we have proven that our analysis is sound. And we have also implemented it in OCaml. And so in the implementation, one of the things that we wanted to see was whether the performance is good or not. Because, well, in theory, the disjunction could make the performance bad, but we see that in practice, the countermeasures that we took are enough to keep the disjunction small and to have reasonable analysis times. And so the test cases that we used were some code inspired from the ACL4 kernel, but adapted to our simple language, and also some sorting functions. And from a precision point of view, well, for now, to know whether the precision is good or not, we have to do it manually. We have to look at the output of our analyzer and see whether it is precise enough or not. But for all the tests that we have done, our analyzer is, has a satisfactory precision. So if we want to compare to some related work, well, one of the ways of looking at our approach is to say that we do 3 different things at the same time. We handle programs that manipulate algebraic types. We are able to capture numeric relations, numeric properties over those programs, and we compute input-output summaries for the programs that we analyze. So this way of seeing our approach helps us to compare to some related work. So if we look, for example, at the compositional recurrence analysis from Farzan and Kincaid, they compute input-output summaries. They capture numeric relations. They even capture nonlinear numeric relations, which is rare in the literature. But they do not handle programs that manipulate algebraic types. If we look at correlations from Andreescu, Jensen, Lecuyer, and Montagu, they compute input-output summaries for programs manipulating algebraic types, but they only handle very simple numeric relations, that is equality between a part of the input and a part of the output, and in particular, they do not handle arithmetic operators nor inequalities. And if we look at the domain for trees from Journeau, Minéa, and Wajau, they handle programs with algebraic types, and they are able to capture numeric relations, but they do not compute input-output summaries. And so, yeah. To conclude, our approach is generic in the sense that we can start with any abstract numeric domain and extend it. It allows to compute input-output relations for the programs we analyze. Those programs can manipulate algebraic types. We capture also numeric inequalities about those programs. We have implemented and tested our approach in OCaml, and we have proven it correct on paper. And some of the limitations that we have is that we do not handle arrays, nor recursive types, nor higher order functions. And we are currently working on adding functional arrays to the language that we analyze. Thank you very much for your attention. And if you have any questions, I'll take that.
So this looks really interesting. It seems very similar structurally to what I've seen in separation logic-based analyses for heaps, particularly how you choose to represent the kind of subfields of the algebraic data types. And I'm wondering if you have looked at those and the way that they've handled things like in particular recurrences in order to be able to handle things like recursive types. Like it seems like you could borrow ideas from inductive definitions for separation logic to maybe start to handle recursive types.
Okay, yeah, that's an interesting remark. And yes, indeed, I think that there is some common theme with separation logic. That is that program logics, and in particular separation logic, also look at the input-output behavior of a program because well, you have a precondition, you have the program, and you want a postcondition to hold. So indeed, it is kind of there's a common framework in a sense. And yeah, we haven't looked at separation logic and how they handle recursion. So yeah, we'll definitely look into that. Thank you.
Hi, thanks for the nice talk. So I had a question about the disjunctive completion, and I was wondering if it was useful only to improve precision, or if it was necessary because you cannot implement some of the transfer functions without it, and as is the case in some shape analysis based on separation logic, you have this problem also.
Okay. So, well, yes, I guess that Yes, I guess that is mainly a matter of precision. Sorry, I guess it's mainly a matter of precision. But basically, if you don't have disjunctive completion, then as soon as you have a pattern matching, you would have a top as a result. So I guess that it's such an important precision requirement that it almost becomes necessary. Yeah, in a way.
Yeah, hi. Thank you very much for the talk. I was wondering as well about your ideas on handling recursive types. And so I was wondering, like, is it possible to do an abstraction on your domain of paths, like dealing only with bounded paths or regular paths, or is it an approach that leads to issues very quickly?
Okay. Yes. So, indeed, indeed. Yeah. When thinking about what we could do for recursive types, we had thought about bounding to some depth, and that would work, but we haven't done it. And we were thinking, well, yeah, we also thought about having regular expressions as paths. That will be a little bit more involved. We didn't, we haven't thought that much about it. Yes, basically for now we haven't thought much about recursive types, but those two ideas could work. The first one, my intuition is that it will definitely work. The second one, I think it will need more thought. Yeah.
Okay, so let's thank the speaker.
Thank you.